Cool. Okay, folks, welcome to the June Northwest C++ Users Group. Got a little delay here as we had some technical problems, got them solved. So I'm going to be very brief on this. First off, I want to thank Conan and JFrog for providing our Meetup account, and thank Microsoft for providing the room and the technical support, which definitely needed some of tonight. I am looking at starting to get pizza going again. If anybody would like to volunteer to help with that, let me know. It's basically, contacting recruiters and stuff. So in the next month or two, we'll get that spun up again. And with that, I'm going to go ahead and hand it over to Brett. Topic is using the power of assembly to fine-tune an application's performance. Thanks.
Yeah, well, we definitely needed that tonight, but but we're here. So as Lloyd had said, this is going to be talking about inline assembly, but this is not just one time that we're going to be talking about assembly or the hardware or OS internals, other issues. So I've talked to Lloyd and said, hey, I want to do a series on this and keep talking about different ways to improve your performance by using inline assembly. So last year there was a couple of talks on C++ and how they were thinking of trying to move away from its roots of C and trying to make a more Python type language so that it would be all encapsulated into a C++ module. And I was thinking about this and I said, yes, but there are some things in C that should be kept in C++. And one of those is inline assembly. Inline assembly can be used to help improve performance of the code. And if you understand the architecture that you're working on, you can utilize some of the features of the architecture. You can use atomic locks and other types of processes that basically C++ doesn't take care of because of the fact that it's more of a higher level type language.
Just a second. I'll mention that screen is not presented.
It's not?
Please renew the presentation, screen sharing.
Yep, I see it.
Still technical difficulties.
You have it now.
Just a sec. Yeah.
Okay, thanks, Rob.
That's good.
So in this particular presentation, we're going to just go through the basics of inline assembly and how it's constructed and some of the examples of how you use different constraints and in the process of making inline assembly in your code. So we're going to look at the code portion, and then we're going to look at the different sections, the output, the input, and then the clobber section of the ASM statement. And then we'll go through some of the pros, and of course there's always cons, and then we'll wrap it up with the conclusion. So, like I said, this is a series. This is going to be, the first one's going to be a primer on inline assembly and how to construct it, and some of the constraints that you can use to use it inside code to do particular tasks so that you can improve performance. And so, like I said, there will be discussion about the assembly and its language. And then we will just talk about how to implement it not only for the current app user layer, but also for the kernel layer. And then down the road, we'll talk about hardware architectures and how to implement it based on the hardware registers. So like I said, this is part one, and it's about inline assembly. And first, we're going to talk about its construction and then give some examples, and then things to consider when implementing. So let's discuss a little bit about why we would want to use inline assembly. So like I said, there's kernel level where you're working with low level IO to handle data from external devices as well as interrupts and the OS. And then there's the user layer. And for x86 architectures, there's a descriptor privilege level 0, which is used for kernel level. And there's also 1 and 2, but I think that they've gotten rid of that because of all the entanglements that can occur with that, checking which DPL to work with. And then there's the supervisor mode, which is for like ARM-based architectures. And then for the user mode, the DPL is 3 or user mode, depending on if it's ARM or x86. And the kernel, like I said, is basically OS, interrupts, and device drivers type code. And user code is like applications like PowerPoint, Word, and other software applications. Now, one of the things is that C is a language that can be used for kernel code. C++ was really more designed for the user level. And part of the reason why C was designed was it was basically comments that were made in assembly, and basically it was converted from like a compare jump to if then. So now let's look at x86 type of memory layout for the segment descriptors. And since this is basically a 64-bit example, it actually uses two 32-bit registers. And basically these registers are saved in a global descriptor table or interrupt descriptor table or some kind of table on the hardware that is basically used for software to find out where an application starts and how to execute that particular code. But we really want to look at this part, the access byte, and understand what that means in the sense of how to design inline assembly. So we have here the access byte with bit 7 as the present bit, and then we have read write in the first bit, and then we have is it being accessed in the bit 0. But in bit 5 and 6, we have what we call the descriptor privilege level. And that is what is used to define which type of software is able to run. So if you're working with the OS, then you want to work with the DPL of 0. So here we go to a nice chart of how the assembly statement syntax is written in C or C++ code. And so we have here the keywords that are noticed by the compiler to say, hey, we're going into assembly code. And then we have the layout of how the string is, or how the assembly is laid out for C to say, or C++ to say, this is what I do with this particular statement. And then we have input and output, and basically we have this nice flow of how it's constructed. So we'll go into more details about that. So over here, we have the keywords that are used for the compiler to know that we are going to be entering an assembly code type definition, and the compiler should assemble or compile this code to basically be inlined into particular operational code in C or C++. And one of the keywords is either ASM, underscore ASM, or underscore ASM, underscore. And of course, we have then we have the volatile, which tells the compiler to turn off optimization on code so that it doesn't get discarded in cases, and we have an example of that later. So now we go to the way it is formatted. So we have the code format string, and basically it's similar to a printf statement. So you basically type in your code and you have your places where variables are going to be inserted by the compiler, and then that will either go into the output and it definitely takes input. Oops. Let me click. And then we also have the clobber section. But these three are optional, so you don't have to write that in your particular inline assembly code. So like I said, the code format is similar to a printf, and here we have an assembly code that's basically entering from the user mode to the kernel mode. As you see, there's no output, input, or clobber variables. It just runs straight up as written. However, sometimes you will need the word volatile with the ASM in order to make sure that we minimize compiler optimizations. As you can see here, that the person wrote the same code in both sections. So the compiler, without the volatile, may discard the second version of the ASM inline assembly code. So this may be an issue because when you're wanting to see what's going on with the registers and you do other work in between there, and you see in the comments, it may have changed the machine status register. And so if the compiler didn't see the volatile, it may get rid of the second one. So therefore the print statement would show what was this statement up in the first block. So sometimes you can use volatile to tell the compiler to turn off the optimization. So there's different now we're going into the output, input, and clobbers section. And we're going to first discuss some of the modifiers that you'll see, especially with the output, but you may see this on the input side. And that is, you'll see an equal sign, and that indicates that the operand is a write only for this instruction. So when you see the equal sign, you'll say, oh, this variable will be written to at the end of the assembly execution, or during the assembly execution. The and sign indicates the variable is an early clobber operand. So that means that the value that you're passing into the inline assembly will actually get clobbered, and a new variable will be coming out on the output. Or it'll be modified during the execution inside the assembly, so that value will not be existing what you've inputted into the assembly. And then you have a plus sign, which indicates that the operand is both read and write. So let's go through some of the constraints that you will see in the definitions of the variables that will be inputted and outputted. And one of them is the R symbol. And the R symbol stands for all registers that you will that will be used within the inline assembly. Sometimes you'll see A, B, C, D, and capital S, capital D, and that reflects different registers. So therefore you would see those particular registers value, or the values that you would be trying to get from the assembly is going to be stored in these particular registers. So let's do an example here. So here we have a output with an equal R, and that is the sorry about that. The RET variable that was defined up here by the uint32. And that will be written to, and then it will be returned at the end when this function is completed. A G stands for either a register or a memory, and that is put in from the input variable. And then you have an offset, and that's going to be set to a register. And so I believe that would be number 2 here. So that would be this offset would be added to the move for number 2. So that would be put into a FS segment with the register that's used to point to some kind of memory. So another example here is that we have A. So this means that the EAX register will be updated and be written to the foo variable, and A will be put in as also the foo variable, and B will be put in as to the EBX register, and that will be put into bar. So therefore we have this add function, the EBX bar plus EAX, and we get the result into the EAX register.
A question. I'm not seeing, I presume you're using your pointer to point at what you're talking about, but we're not seeing the pointer on the output. I think there's a mode that you can set.
I'm using a mouse, but I'm not sure.
Yeah, I don't know if we've got a pointer on this. Let's see. Yeah, the pointer's not coming through on the connection.
Not seeing it either.
No, we don't see it in the room either, so.
I know, I'm like,
Oh,
what's
well.
going on?
Yeah, I'm sorry about that.
That's why we have like 20 months, to figure out all our problems. So there are more constraints that are defined by GCC. There may be constraints defined by Clang or other compilers, but here are the most common constraints that are generically used, and one is the M constraint, which is used for like a memory operand. It's like a memory address or a pointer. O is like an address that is offsetable, like a pointer to an index inside of an array, or an array with the index of that particular memory location. V is also used for memory, but it is not offsetable, so it's therefore a pointer to a constant pointer, as an example. An immediate I for an immediate integer, which usually has a constant value. N is a numeric value. And again, G as a general register or memory operand. And of course, there are many more based on different hardware architectures. Like you can have different constraints for like the Spark, or you can have constraints for Atmel or something like that. So let's do a little example of the R constraint. And I think we just did something, but let's do another one. So here we just have the R. R means that it's going to any register. It doesn't matter which register will be used to be updated, but in here we are moving the source to another register, and then we're adding the two, and we're putting that result into a destination variable. Like I said, it's a generic register, so we don't know which register will be updated, but we know that a register will be returned and into the result. Here we're using a memory variable, my var. So we're putting a pointer in here, and we're updating the address of the pointer And when we get the result back, we should be getting the address of my bar that's been updated. Too fast, too slow? Okay, here's an example of an offsetable operand. So here, like I said, we have swap vals of the index. So swap vals has a particular address, and the index basically points to one of the values. If you look in the top there, it says that there's 8 values in the array. So we point to one of those values in the index, and now we have the plus O, so therefore we're going to be updating this particular value in the swap vals. And that's why the O is used, because it's offsetable for that particular index. So now we're going into the Clobbers section of the inline assembly. And basically it indicates that registers inside the inline assembly may be overwritten. Each item is in the list is surrounded by quotation marks and separated by a comma, as you saw in that wonderful diagram. And there are special clobbers that are used to help facilitate writing an assembly statement. There's the CC, which is used to define that a flag's register will be updated in the particular code. So therefore it will be clobbered before it's actually the execution of the code is completed or started, because you want to make sure that there's no residual values that are being used in the particular execution of the assembly code, so that you won't get funky data. And then there's a memory, it's a value, which basically tells the code that the code performs a read or write to the operands, and that the compiler needs to flush the register value before executing the ASM code. So let's give a couple of examples here. Here we have the Special Clobber CC, and what we're doing here is we're clearing or setting a bit in a register. So basically, this can update the overflow flag or the negative flag. So we want to make sure that any bits that were in the flag before it was executed is actually cleared out, so that when we get the results back of a flag issue, we know that it is correct when we're completing this particular ASM code. And now we have an example of early clobber with the special clobber memory. Here we're doing a string copy. And here we have the equals and S, which is basically the ESI register. And we have the equals and D, which is the EDI register. And we have the equals and A, which is the EAX register if we're working with 32-bit. So basically, what we're trying to tell in the early clobber is that this variable will be updated, and therefore it needs to be known that that value will be changing as it goes through the block of copying the characters over from the source to the destination. And then excuse me, sorry. And then we have the memory variable clobber here, which again, since we know that we are going to be working with particular registers, the compiler will know that it should be flushing the memory registers that will be the in here the AL register, to make sure that that it has pre-filled data that may affect the operation. So what are some of the pros? Well, you can optimize your performance. For example, we're in the string copy code, it was using the CPU registers, but maybe you want to use the GPU registers to do the string copy. So therefore you can do multiple character copies at one time rather than just one at a time. So that's one of the values of doing inline assembly. So we're not relying on the compiler's interpretation of what your code is supposed to be doing. You are therefore in control of how you want this code to be executed. You can modify how your code is executed. Again, like I said, if you don't want to use the CPU to do your particular operations, you want to use some other type of external processing unit, you can do that, or you can do things that maybe you want a atomic lock-free queue. So you can probably do something there that may be more efficient than what the compiler is giving to you. And it allows you to access device driver data. So you can do some IO operations where you, in regular C++, you don't have that ability because you're working on a different security layer. Like in this example, we're getting an in byte from a particular port. And so therefore we can call this particular assembly command NB and get a value from a device driver that you couldn't get from a particular C++ application. So therefore you can access data much quicker than relying on other APIs that C++ may provide. Of course, there's cons to everything. You need to make sure the code is written correctly. Because it's like a print statement, if you don't write it correctly, you're gonna be sitting there going, what's going on in this particular piece of code? Why is it not performing the way I want it to do it? So that's something that you have to think. So it's not easy to debug because again, you're writing basically a string and you're saying that this is what you think the string should be doing, but you're not gonna have like step through the code to see exactly what's really going on. So now it's your turn. So what would be wrong with the following?
It clobbers EBX and doesn't say that it's clobbering EBX. It also clobbers EAX and it doesn't say it's clobbering EAX.
Okay.
Another thing is int 80 might have the effect of clobbering some other register. You'd have to actually read the kernel documentation to find out.
Okay. So those are very important things, yes. But more of a high level, you also have to know that this may not, if you compile it for an Intel compile, it may not work because you're working with AT&T syntax, or you're working with x86 architecture and not ARM architecture. So therefore, you have to consider so therefore you can't just write one blanket piece of code and expect it to work on all platforms. So you're gonna have to consider the hardware that you're working with. But yes, thank you.
Right. The other thing is, of course, this is assuming that you're using Linux, basically, because Linux has sysexit as one on Linux. Yeah. That's not necessarily true for anything else.
True, that is true. Thank you. So, in conclusion, I went fast. We just scratched the surface of the power of inline assembly. We can use it to enhance the performance of C++ type applications. We can also use it for Rust and other other software languages. We can access low-level data using regular C++, where regular C++ applications cannot. But like I said, you need to know your environment. Like it's Linux, or are you working on Windows, or you working ARM, working x86. Since it's put in a string, it must be written carefully. However, once you know assembly language, it opens the opportunity to improve many aspects of your code development and execution. So thank you for coming. Any questions or comments?
I have a complaint about the way inline assembly is currently implemented in C++.
Okay.
I am currently in the process of trying to write an alternate set of wrappers for the system called API for Linux.
Okay.
And one of the things that I really want to do is be very careful about telling the compiler about exactly what's being clobbered, including like what regions of memory need to be paid attention to, so that the compiler can do the best optimization it can, because everything is going to be inlined. And so all these, like, everybody's like, oh, you don't inline system calls, why do you even care? Well, actually, if you inline them the right way and tell the compiler exactly what memory and registers are going to be fiddled with, the compiler can optimize across the system call much better if it has all that information available to it and it's inlined. The problem is that there's a whole lot of different ways, things that can be clobbered in various ways. I don't want to have to write a custom piece of inline assembly for every single system call.
Okay.
And I can actually use type information in the C to say what's going on. And if I had a decent templating mechanism that could output inline assembly, I could actually make the type information that I have in C++ result in the correct set of clobbers in the inline assembly output.
Okay.
And right now I can't do that.
So you're essentially proposing templates for assembly language.
Yes.
Yeah, I've seen that done before. Microchip assembler does things like that with macros and templates and patterning. It can get pretty powerful. It also can, like templates, get pretty hard to read.
And I'm afraid that like templates can also be put into different locations that isn't easily accessible to all the code that needs it. So yeah, templates are a bane of C++. They're useful, but they're to the user, they're a code developer.
No, I don't think you'd use the general templating mechanism.
Yeah, so.
That's interesting.
Well, I've been working on a couple of C++ proposals myself and on interrupt handling and event handling. And I was like, how am I going to do this? So one morning I just got up, I said, inline assembly, that's it. So that's why I thought this will help me get to that end. So thank you, Lloyd. I have some references. I may be updating them. So once I get the slides to Lloyd, I hopefully will have everything there.
Okay.
And thank you very much, everybody.
Okay. Any other comments? That was we got a little extra time here. We don't get kicked out till 8:30, but. Robin, so we go ahead and kill the video at this point?
Okay, just a sec.